All right, howdy everybody. How are we all doing tonight? Today I'm going to give a presentation on Statechains, and let me pull that up for you so that we can dive into my latest idea for how to improve Bitcoin. My name is Super Testnet. I am a Bitcoin developer, independent freelance software developer. I focus on Bitcoin, the Lightning Network, Statechains recently, a lot of prototyping and development of layer 2s for Bitcoin, new ideas in that space. Today I want to talk to you about Statechains and maybe even do a little demo of how they work and an idea I came up with for fixing what I identify as some of their biggest problems. So let's talk about what Statechains are. This is a picture of some agents of the state that have been chained together. Statechains, that's the best I could come up with as a visual pun. But we're going to talk about what they are. We're going to do some benefits and drawbacks of Statechains. We're going to do some of the drawbacks, how I've thought of fixing them using an insurance protocol that I designed. And then I'm going to do a conclusion. So, ready to get started? Let's do it. So, what Statechains are? Well, we got a little visual indicator of what Statechains are up here. We've got Alice over on the left and Bob on the right. And we got somebody in the middle who I call an operator, a Statechain operator. So Alice, she has a coin worth 50,000 sats, and it's locked to a private key that she has control over. And on a Statechain, if you want to transfer money to somebody, this is actual Bitcoin locked to an actual private key. You don't create a Bitcoin transaction with a Statechain. Instead, you directly send the recipient the private key to that UTXO. So Bob has it now, and he says, "All right, thank you, Alice." Well, Alice's private key, which she just sent to Bob, is not the only private key involved. In Bitcoin, you can have a multisig. You can say two private keys control the same money, and both of them have to sign off on whatever happens to that money. So Alice had one, and this blue guy down here, he's the operator. He had the other private key. So once Bob has Alice's, he talks to this guy, and he says, "Hey, don't talk to Alice anymore. Only talk to me. I'm the holder of the private key now. And so if Alice wants you to sign a transaction or anything, don't talk to her, only listen to me." So the third-party operator here is the person who prevents double spends. He prevents Alice from taking the money back by saying, "Prove you're Bob." And of course, Alice can't prove she's Bob, so the operator's just like, "No, you're not allowed to have this money. Only Bob can have this money." And that's the basic idea of a Statechain. A trusted third party holds a second key to that money, only interacts with the latest holder. Of course, the question is, why? Why would you do this? Why would you come up with this complicated protocol involving a trusted third party when we've got Bitcoin, and Bitcoin solves all the world's problems? Well, there's a couple of reasons why we might do this. Oh yeah, I forgot about this part. Before I get into why we would use them, I have to talk about decrementing time locks. Here I use the example of a check. A check is kind of like a Bitcoin transaction, in that like a Bitcoin transaction has an address you're sending from and a destination. And here that's like this guy's bank account is kind of is the address that you're sending from, and then who it's going to Alice up there. So it's kind of like a Bitcoin transaction. There's a sender, there's a recipient, there's an amount up there. So I'm using checks to represent Bitcoin transactions on this slide. You guys with me? Checks are Bitcoin transactions. Sender, recipient, signature, amount, that stuff. So what we do is, in a Statechain, whenever, Alice was the first person to have the money, she has with her with her private key and with the operator's private key, she got the operator to sign this transaction that sends whatever amount of money is in that UTXO, 50,000 sats in the previous example, she gets him to sign a transaction that sends it to her. But the part up there where the date is, that part's important. In Bitcoin, we have this concept called time locks, which also exist on a check. You can post-date a check for a future date so that someone's not able to cash it until that future date. You can do the same thing with Bitcoin. If you use the time lock field in a Bitcoin transaction, you can prevent somebody from cashing that or from redeeming that Bitcoin transaction, from actually broadcasting it, until the time lock arrives. So what we do is, Alice has one that's far in the future. I've got hers set to December 31st, the last day of this year. And when she sends when she sends her private key to Bob, Bob gets the operator and himself to sign a new transaction that has the same amount. It's still just giving him however much money is in that Bitcoin address, but it's got a lower time lock. So that means that Alice can't go first. Bob can always redeem his check before Alice can redeem hers. And so if Bob wants to send to Carol, we do the same thing again. Carol has the operator sign a new transaction, giving her the money with an even lower time lock so that she can always withdraw her money before anybody else can. So that's called decrementing time locks, and we use those in state chains. The reason we use these is because we don't want this to happen. We don't want this guy to die or blow up or get hit by a bus or his server gets confiscated or something, and then Bob can't withdraw his money. So what we do is we make it so that the first thing Bob does is he gets him to sign one of these checks, and then even if the server goes away, it's fine. He's already got the check. He's already got a signed Bitcoin transaction, letting him leave whenever his time lock arrives. So that's why we use decrementing time locks in this. Now, what are the benefits? What are the benefits of doing this weird thing with an operator, a trusted third party, and decrementing time locks, and we've got this beautiful Bitcoin protocol? Well, there's a few benefits over here. It's faster than a speeding bullet. It's actually faster than Lightning to use a state chain, usually because you don't have to do any pathfinding. I don't know if anyone's ever used a Lightning transaction before. How many of you have used a Lightning wallet? Most of us, okay. Have you ever had a Lightning payment get stuck? Yeah, several of us have had this happen. When you send a Lightning transaction, your wallet has to find a path from the sender to the recipient. It has to find, if you don't have a direct channel with them, then it's like, I'm going to check and see if you have a channel with, async. And if you don't have a channel with async, maybe you have a channel with Blockstream or whatever. But doing that pathfinding takes time, and it can result in the channel getting stuck. On a state chain, you never have a pathfinding problem. Whenever you're sending money, you're just giving somebody a private key. It's just a piece of text. You just send it to them, and then they have the money. And so it's faster than Lightning in that respect. Usually, it's also cheaper. The implementations that exist don't charge fees for transfers. So Lightning does, and these don't. The only time Lightning would be equally fast is if you have a direct channel directly to your recipient and there's no pathfinding involved. Then Lightning is just as fast and just as cheap because you don't have to pay fees in a channel that's direct. So normally, state chains are faster and cheaper than Lightning. They also use a blind server. When you tell the server, here's a proof of who I am, he doesn't actually know anything about the transaction he's signing. He doesn't even know the amount. So it has a similar blind server property like eCash, represented over here by this nice blind lady. And you also have semi-unilateral withdrawal. That's because of these checks right here. You have a signed transaction every time you receive a state coin that lets you withdraw. And you can do that even if the operator goes away, because it's already signed. So you can withdraw even if the operator disappears, which is nice. So those are the benefits of state chains. What are the drawbacks? What's the problem? If it's such a good idea, why isn't everybody using state chains? Well, there are some problems. One problem is fixed denomination, which I represent with normal money, has fixed denominations, like you have a 20, you have a 10, you have a 5. You have to do the same thing with a state chain. You create actual UTXOs with a state chain, and it costs money to do that. In order to put money onto a state chain, you have to create a UTXO. In order to take it off, it costs money. There's also double spend risk, which is where, well, I'll show you that in a minute. And state chain UTXOs expire. The expiry happens because, let's say that you start off with Alice and her withdrawal time is at the end of this year, and then she sends it to Bob and it gets a little closer to today, and then Bob sends it to Carol and it gets even closer to today. At some point you run out of days. Like at some point you're going to have a check or a transaction written that's cashable today. And at that point you can't really transfer it anymore, because what are you going to do? Go back in time and give it to someone before today? You can't really do that. So they sort of expire. Like you have to, once this date is reached, for Carol, if she still has the money, she's got to broadcast it because she can't really transfer it anymore. Otherwise, the recipient would be like, I'm not accepting a check that says you can withdraw at the same time and I can withdraw at the same time. That's really weird. So they kind of expire, which is another problem with state chains. To illustrate what I think is the problem I have not solved, this is the problem I have not solved with my solution, fixed denominations and costly base layer transactions. Well, here's Alice again. Let's say she wants to use a state chain. So she's got a Bitcoin over here. She deposits it onto the state chain, which just means putting it in a multisig at Bitcoin address. There's a fee associated with that, right? So this Bitcoin transaction, he goes into a multisig and he's like, that costed something. That costed you 5,000 sats to do that. But okay, she's got a Bitcoin in here. Now she can transfer it. So she says, I've sent the whole UTXO over here to Bob. It was on her side. Now it's on Bob's side. He's got a copy of the private key. He gets his little check, his withdrawal transaction. But once again, there's a fee. If he wants to withdraw that money, if he wants to broadcast that transaction, he has to pay a fee, perhaps 5,000 sats. Well, so that coin, in essence, it's worth less than what its face value is, right? Because it says it's worth a Bitcoin, but there's a cost to deposit it and a cost to withdraw it, and you have to take that into account when you're receiving it. It's worth slightly less than what it says. So that's kind of a problem. And the other thing is, you have to transfer the whole UTXO. She can't send him half of this thing, because she's not creating a real Bitcoin transaction. She's actually sending him a private key. So she has to send the entire thing, which means in order to use Statechains, you kind of got to do, like let's say you make a 5,000 sat UTXO and a 15,000 sat UTXO and maybe a 50,000 sat UTXO, and you have to treat them like physical bills and then like give them out and try and get close to the amount you want. And maybe that person can then send you another UTXO that's worth some of the change. It gets messy, but that's kind of what you have to do with them. So this part's kind of expensive, depositing and withdrawal, because it involves a base layer transaction, and you don't get normal ways of doing change in Bitcoin. So those are some drawbacks. My solution that I'm going to talk about today does not fix these two things, but it fixes the next ones. So this one is the double spend risk. So how does double spending work in a state chain? Well, let's suppose we have Bob. He was the second recipient. He got this coin over here from Alice. Well, what if Alice keeps her copy of the private key, right? She was supposed to send it to Bob. Maybe she kept a copy. Now, it's not enough for her to do anything with it on her own. One private key is not enough to do anything with a Bitcoin locked to a 2 of 2 multisig. But the operator, maybe he kept his key too. And if he kept his key and she kept her key, well, now you're in trouble, because Bob thinks he has this money, but if they've got both the keys, they can just take it down here and then like divide it up amongst themselves or something like that. So Alice supposedly sent the money to Bob, but if she is evil and if the operator is evil, they can take the money back. This is called double spending. Guess what was invented to fix the double spending problem? Bitcoin, yeah. So we're back in the old days of Bitcoin. Well, I figured out how to fix this. And so that's what I'm going to show you today. The other thing is the Statechains UTXOs expire, but I forgot that I made this slide, so I sort of already talked about how that works. So we're all good on the expiry? Yeah, okay, thumbs up I'm seeing, great. Okay, so my approach to fixing the first problem, the double spend problem, is insurance. Insurance fixes this. So here we've got Carol. Let's suppose Carol is the current holder of the coin, and she doesn't want to be robbed. She doesn't want to have the risk of an operator coming in and taking her money from her. So what she does is she hires this guy. This is going to be Ichabod the insurer. There aren't that many names that start with I. But he's going to be Ichabod the insurer, and she's going to pay him a monthly fee to take on the risk for her. So that if this check bounces, if the Bitcoin transaction that is supposed to come to her becomes invalid, like the operator sent the money to the wrong person, if that happens, he has to pay her money in an equal amount. So in this case, $2.56. Why did I do $2.56? It's kind of a power of 2 number right there. That's why I did that. But yeah, he has to pay her the money instead. Now, how do we enforce this in Bitcoin? The way I do it, the method for enforcing this, is what I describe here. That's Carol over there. This is the insurer. The insurer is not the same person as the operator. They could be, like it doesn't hurt anything if they are, but I thought it'd be fun to make them different from the operator. So they're going to create a 2 of 2 multisig. Sounds familiar. We've been using those all over the place. And he's going to put the same amount of money she wants to insure or more. So in this case, she wants to insure the $2.56 that's supposed to come to her from this Bitcoin transaction. So he is going to put more than that in this case. He's going to put $5 into this multisig Bitcoin address. But before he deposits that money into this multisig, before he does that, they do this. Now, if any of you are not familiar with technical Bitcoin specifications, this is how Super Testnet draws Bitcoin transactions when he's not representing them as checks. And it's a little confusing because I'm also representing another Bitcoin transaction as a check here. But Bitcoin transactions, they all have inputs and outputs. This is like who's sending the money over here and who's receiving the money is over here. So what we're going to use as the input for this Bitcoin transaction that the insurer is going to create, we're going to use the insurance address, which is about to have $5 in it. He's going to use that as an input, and he's going to use the money that's supposed to come to Carol. But instead of just coming to Carol, that goes into a 2 of 2 multisig as well. Lots of 2 of 2 multisigs. That's the only way to do this, like enforcing where an output goes in Bitcoin. So I use it all over the place. But this is a 2 of 2 multisig. It's got $5 in it. This is a 2 of 2 multisig. It's got $2.56 in it. And as outputs, what we do is we let the insurer get his $5 back, and we have Carol get her $2.56. So it's almost identical. The input side and the output side are almost identical. The same amount of money is going to the same people here. But here's why we do this. Because there's another path. This path, the one that I show here, this happens as long as this check, as long as this Bitcoin transaction is redeemable. This is the one that's supposed to pay Alice. So if this money gets on chain, that means that the operator did not send it to the wrong person, so we're good. We can just give the insurance provider his money back, and we give Carol her $2.56. If that does not happen, we have this second path right here, which is the same Bitcoin address, the insurance address, also allows Carol to just spend that $5 on her own if 6 months go by. And what that indicates is if 6 months go by and she didn't get her money, well, the time's up. Like something must have gone wrong. The operator must have sent it to the wrong person. He must have colluded and done the double spend thing I was talking about earlier. Because Carol was supposed to get it once the time lock arrived. But she didn't. So there's a problem there, and that means that we have to do an insurance payout. So if this check never cleared, then the operator cannot broadcast this to get his insurance back. So after 6 months, Alice gets the insurer's money. So the result of all this is this situation. If Alice does not get robbed, she's happy, the insurer's happy because he gets his money back and she gets her money and nothing went wrong. They're both happy. Otherwise, if Alice did get robbed, if the operator double spent and sent the money to the wrong person, Alice is still happy because she got the money from the insurer, but the insurer is sad because because he lost his money. He insured something that was not a good thing to insure. So this is a protocol for letting us create insurance contracts in Bitcoin script, and makes it so that this guy takes on the risk. And so if he is willing to do this for certain state chain operators, and he's like, I don't think this guy will rob people, he can actually make money by charging a fee for this service, and then she doesn't have rug pull risk. So that's the idea for fixing state chains. Before I get to questions, I want to do a demo. I want to do a demo of this software so you can see what it looks like. However, the demo doesn't do this part. I don't have the insurance part implemented. I just have a state chain implemented that'll be compatible. We have a question first? I couldn't hear you. Oh, the question is, what is in it for the insurer? Well, Alice pays him. She would pay him a monthly rate for him to continue providing the service. And so, Yeah, she just pay him with a lightning payment or something to keep providing insurance for her. So that's the answer to that. So I want to show you a demo of how this works, and I got the demo working today, so hopefully it will still work. Let me pull it up. It would be in Bitcoin projects, I think. No, GitHub projects, that one. So I open up this. Oh, and I have to clear out my cookies because this is what I was doing earlier. Local storage.clear, and then reload the page. Okay, so I'm going to show you how this works. This is not very pretty. The demo I'm going to show you is not intended to be pretty. It's intended to be very simple and to have a very small number of lines of code so that other engineers who are better engineers than me can make this work in a classier way. But I'm going to deposit some Bitcoin onto this little app here. So it's going to show me a Bitcoin address. And I'm going to do this on Bitcoin's, on a testnet that I've spun up on my own little computer here. So let me do that. Let me send to address, paste that in, and I will be sending 10,000 sats. Now you guys can probably barely read this. I can't really make it very big or anything, but it says send to address, and I paste it in the address, and I'm sending 10,000 sats into that. So I do that. It gives me a Bitcoin transaction, and if I take a look at that transaction, obviously this is not how a normal app would work. You would not be showing your users a command line interface for doing this stuff, but for demo day, that's the best I can do. So we have two outputs here. This is the output that pays 10,000 sats to the user, and then this gives the change back to the faucet. So I'm going to paste into here the transaction ID and the vout and the amount. All of this should be done through an API, but if I had done it using an API, it would have increased the amount of lines of code by 400. So I'm just copy pasting to keep the number of lines of code small so that developers can actually see what's going on here and not have to sift through all that. So I'm going to submit that, and now we've got a 10,000 sat Bitcoin UTXO. I can even label it and be like, I made this for a demo. You can label your UTXOs in this thing. Let me make that a little bigger so y'all can see it better. Now what we were really interested in here is adding this coin to a state chain. We want to see him deposit this money, which is currently on regular Bitcoin, to a state chain. Before I do that, I want to show you how silly Super Testnet is. This is the private key right here. This is the private key to that Bitcoin UTXO. So don't do this. Don't put your private keys in a cookie on your web page. Actually store this stuff encrypted or something. But this is just a demo, not for, don't use my code, use the idea. So I'm going to click and deposit this onto a state chain, and it needs something called the end profile of an operator. I decided that I didn't want to implement a peer-to-peer network for this, so I'm using Nostr as a replacement for a peer-to-peer network. So I'm going to run an operator over here by clicking this button. This is like an explainer for how state chains work, but I just explained it to you in the thing, so I'm not going to read all that. But I'm going to run an operator in a private window here. Come on. This is the part where I worry. If this doesn't work, the demo won't work. All right, I need all you to put your hands up in the air like Goku. We're going to make the internet come down and rescue my demo here. Come on. The powers that be are not with me today. Shucks. I'll give it one more try. Refresh this. Oh, look, it worked. Oh, thank you. Thank you. Yeah, okay. So I'm running an operator. Escape that. And so I'm going to paste his profile right here. That's what I'm going to use as my operator. It warns me, hey, this operator could steal from you. You probably can't read that. It says this operator can steal from you. You have to be sure you trust your operators. Well, once I implement the insurance thing, you won't have to trust him anymore, which is really the important thing that I think is, I want to get rid of this pop-up. I don't like this as a user experience thing. With insurance, I won't need it anymore. But I'm going to click OK. I do trust him because he's me. And I'm going to create 4 StateChain UTXOs. So I had 10,000 sats on actual Bitcoin. I'm going to take 500 sats and use it as a fee. And then the rest I'm going to create StateChain UTXOs with. So I'll submit that. And here we go. It is now communicating with the operator to get him to sign those little checks, those Bitcoin transactions that give me my money back. And so right here, we should start to see StateChain UTXOs pop up. And we should get 4 of them that are mine to keep. Cool. So now I've got a Bitcoin transaction that I can broadcast that makes this reality. I'm going to do that in here by saying send raw transaction, paste that. And if I decode that transaction so you can see what's inside, you can see that it created 4 UTXOs, actual UTXOs on Bitcoin, all for the same amount, 2,375 sats. And you can't really, unless you can read the code here, they're all, what's it called, locked to a Bitcoin multisig. And I can show that over here. Each of these things is locked to a multisig. You can actually view the multisig right here. That's the script. This is the user's key. This is the operator's key. So it's a multi-sig. And yeah, so now let's try sending this to somebody. I'm going to open up, I'm going to click send on here. So there's a few things I can do. I can send the coin to somebody, which is what I'm about to do. I could also do something called a cooperative withdrawal, which is where me and the operator co-sign to take the money out. I can also withdraw unilaterally. If the operator disappears and blows up, I can click this and broadcast that little check I have, which is nice. If I do, though, I have to wait because of the decrementing time lock thing. And currently, I have it set to make me wait for 2016 blocks. But what I'm going to do, I'm going to send the coin. So I click that, click send the coins. Oh, I forgot to confirm that. Oh, well, that's as far as we can get. I forgot to implement checking to see if the thing is confirmed, so I can't go any further. But what would happen, if I had sent this, it would have disappeared from here and been replaced with some text, and I could send that to somebody else, and they could click this button right here and import that coin into their own wallet. And there'd be no fees for doing that. Then they would have the little progress bar. It would talk to the operator and tell them, don't talk to the first person anymore, only talk to me. And we would keep doing that over and over again, but the time lock would decrement each time. It would go from 2016 to 2015, 2014, and so on and so forth. At the end, once it gets down to 0, you just have to withdraw. You can't send it anymore. You have to withdraw because no one will accept it if the lock time is 0. Okay, so that is most of my state chain demo, but I forgot to implement a part of it, and so it didn't work. But any questions? Any questions about state chains or insurance or any of that? What do we got? I can't hear you. Come up here and yell. Closer. What stops the insurer from colluding with the sender and the state chain? Yeah, so if the insurer has a set of different keys than the user, if the insurer colludes with the state chain, all he could do if he colludes with the state chain is nothing actually. He couldn't do anything because the state chain only has one key and Carol has the other. So he couldn't really do anything. He could find a prior holder. If he wants to steal from her, from Carol, they could find a prior holder and they could move the state chain UTXO, but that would not move this UTXO. This one would still have her money in here. So once the 6 months are up, she would get the money out of this one. Carol would get it out of here. Correct, that is not on the state chain. That's on Bitcoin. Yeah, so that takes care of that. He can't steal from, this guy cannot steal from her even if he colludes with the state chain entity. Any other questions? What's up? The incentive to be an operator, the way that, so I have an implementation of Statechains here which doesn't charge any fees for anything. There's an implementation of Statechains by a company called Mercury, or no, they're called Commerce Block, but the Statechain's called Mercury. They charge a fee for deposits. So if you want to deposit money onto a state chain, you have to get a public key from them, and they won't give it to you until you've paid them like $1 or something. And that's their fee revenue. They also don't charge for transfers, they only charge for deposits. So transfers are free after that, but that's how they make money. What's up?
You're locking up the insurance Bitcoin for quite a long
The
time.
question was, are you locking up the insurer's Bitcoin for quite a long time? Yes, you are. And he should charge money appropriately to cover the cost of, he could be doing other things with that Bitcoin. Any other questions? Okay, cool. The one thing I want to cover, this is a complicated question that I thought of. Oh, we got one over here.
Sorry, just a question. Could this be used for like sale of fractional real estate?
A fractional what?
Company? A title company. Couldn't a title company use this tool to fractionalize sale of pieces of real estate ownership?
Most things are possible if you try really hard. I don't know how to solve that problem off the top of my head, but probably. Sure. So here's a complicated question, which to me is an important one, but it's really hard to get across. Why is this bigger than the $2.56? Why is this bigger than just the exact amount that he's going to insure? The reason why I have this bigger is so that she can receive more money on the state chain without needing to bump her insurance cost. So if she receives another one of those checks, another one of those state chain UTXOs for, another $2, as long as the sum of her money, like she has $2.56 plus another $2, as long as the sum of all her state chain UTXOs are less than this amount, she can insure them all using one insurance thing. All you would do is modify this so that there are two checks here. She'd be insuring both of them with the same UTXO. And I think that makes it more efficient. It would be bad if you had to create a new insurance UTXO for every single transfer. If you can do it less than that, then this makes sense, I think. So that's why I make the insurance address significantly bigger than whatever check you're insuring, so that you can do multiple. Okay, I hope did that question make sense? I hope it's kind of a hard thing to wrap your head around, but thank you for all for coming to my presentation. I hope you had fun, and I'm going to get to work implementing this.